Welcome to Ask and Learn.
We're asked to show that inequalities about the key enclosure of sets hold. So in part A, we're asked to show that the key enclosure of the set containing the empty string is simply the set containing the empty string. Now, we have that the set containing the empty string squared, this is the concatenation of the set containing the empty string with the set containing the empty string. And this contains all strings of the form xy, where x is a string in the set containing the empty string, and y is a string in the set containing the empty string. So it follows that this is equal to the set of all strings xy such that x is in the set containing the empty string and y is in the set containing the empty string. And this is equivalent to the set of all strings xy such that, well, if x is in the set containing the empty string, then x must be the empty string. And if y is in the set containing the empty string, then y must be the empty string. This is simply the set containing the empty string concatenated with the empty string, which is simply the set containing the empty string. And likewise, you can prove this by induction if you'd like. We see that the set containing the empty string to the nth power, well, we know that this is going to be the same as set containing the empty string to the n minus first power concatenated with the set containing the empty string. And we can continue this all the way until we get down to the set containing the empty string times the set containing the empty string, which is the set containing the empty string squared, which we showed already is the set containing the empty string, as long as n is greater than or equal to 2. And so by the definition of the key enclosure, we obtain that the key enclosure of the set containing the empty set is equal to the union from n equals 1 to infinity of set containing the empty set to the nth power. This is equal to the union from n equals 1 to infinity of, as we already showed, just the set containing the empty set, which is going to be the same as set containing the empty set again, because the union of two sets which are identical is the same set. This is what we wanted to prove in part A. Now in part B, we're asked to prove that the key enclosure of the key enclosure of a set of strings A is the key enclosure of the set of strings A again, for any set of strings A. So let A be a set of strings then we have, by the definition of the key enclosure, A star is also a set of strings, and so A star star, this is equal to the union from k equals 1 to positive infinity of a star to the kth power Now, we have that a star squared is the concatenation of a star and a star, which contains all strings of the form xy, where x is a string in a star and y is a string in a star. So we have that a star squared is going to be the set of all strings xy such that x is in a star and y is in a star. Now, a star contains the concatenation of any amount of strings in A. And so it follows that a star will also contain xy when x is in a star and y is in a star. So it follows that this set is equal to a star itself. And likewise, we have that a star to the n, by definition, is going to be a star to the n minus 1 concatenated with a star, and you can prove this by induction, that this is equal to a star times a star, which we've shown, well, this is by definition a star squared, which we showed was the same as a star for n greater than or equal to 2. And therefore it follows that a star star is equal to some, or the union from k to positive infinity, and this is just going to be a star now, and now notice that the union of a set with itself is always going to be the same set, so it follows that this union, even though it's infinite, is still going to be a star. And so we've shown that the clean closure of a star is the same as a star.